Good morning all. So today we are going to discuss few numericals on sampling theorem. Okay, numericals on sampling theorem. So last class we have seen different type of sampling. First, instantaneous sampling. Second, natural sampling, and third, the flat top sampling. Now we will go through the numericals, how to find out the Nyquist rate, Nyquist interval, if a single tone signal is given, if a multi-tone signal is given, depend upon the nature of the given signals, and how we are getting the spectrum for those particular signals. Okay, so let me write the first question, that is, let us consider an analog signal which is multi-tone. Okay, which is multi-tone. Analog signal means consider an analog signal means it is a modulating signal which is a multi-tone, given as x of t is equals to 3 cos 50 pi t plus 10 sin 300 pi t plus cos of 100 pi t. Okay, and here we have to calculate Fs, that is the Nyquist rate, and Ts, that is the Nyquist interval. Okay, now how to identify this? So first of all, we have to see what sort of modulating signal it is or message signal. It consists of more than one number of frequencies. That means it satisfies multi-tone. So from the first part, I can determine F1 omega 1 divided by 2 pi. Okay, omega 1 is how much? 50 pi divided by 2 pi, that is 25 hertz. 25 hertz. Similarly, Ft is equals to omega 2 divided by 2 pi. Omega 2 is how much? 300 pi divided by 2 pi, so it is 150 hertz. Okay, and F3 is equals to omega 3 divided by 2 pi, that is equals to 100 pi divided by 2 pi, so here you will get 50 hertz. Now as we have discussed how to determine Fs. Fs is nothing but twice of F max, maximum frequency available in the given modulating signal. Now you can see which one is maximum. 25 is maximum, 150 is maximum, or 50 is maximum. 150 is maximum. So that means the sampling frequency or the Nyquist rate will have twice of 150, that is 300 hertz. Done. Similarly, what is the Nyquist interval? Nyquist interval is Ts, that is equals to 1 by Fs, which is equals to 1 by 300, this much second. So this you can calculate it with the help of calculator and get it done with respect to the interval. So this is the first question. So like this, Nyquist rate and Nyquist time interval can be determined. Okay, for multi-tone signal. Second question, we are going to discuss a signal g of t is equals to 2 cos 400 pi t, then plus 6 cos 640 pi t. Okay, 640 pi t is ideally sampled at a rate of Fs is equals to 500 hertz. Okay, 500 hertz. If sample signal is passed, if sample signal passed through an LPF, through a LPF means low pass filter with cutoff frequency with FC, means that filter is having the cutoff frequency FC is equals to 400 Hz. Now here we need to find bit A. This is G of T. You need to calculate G of F and its sketch. Sketch means spectrum you have to represent. Then with V, the sample signal, that is G del of F. That means G of T is sampled at a rate of 500 Hz and its spectrum. Okay, and its spectrum. Then C is the component that will appear at the output of LPF. So these are the 3 points which need to calculated with respect to the given data. So step by step we will see. So first here, what are the given data? So as G of T is equals to 2 cos 400 pi t plus 6 cos 640 pi t. Done. And the sampling frequency is given as 500 Hz and the ideal low pass filter response is given as 400 Hz cutoff frequency, and here it is minus 400 Hz, amplitude is 1, and this is H of F. This is the low pass filter characteristics. Done. Now here we need to calculate what is G of F and the spectrum. So G of F means what? G of F is the Fourier transform of G of T. Then, so what is the Fourier transform of this? As it is a cos term, we need to represent in terms of del. That is the property of this Fourier transform. So here it is 2 is the amplitude. For this, it is half of del of F minus 400 omega F. So here omega 1 is equals to 400 pi, F1 is equals to 200, because so here it will be 200 plus del of F plus 200. So this is the first part. Then second part is 6. This is half, and here we can write. So this is for omega 1. Similarly, omega 2 is having 640 pi. So F2 is equals to omega 2 divided by 2 pi. So here I will get 320 Hz. So here I will write F minus 320 plus del of F plus 320. Okay. So this is the Fourier transform. Now these two get cancelled out. This 2 and this 6 will be 3. So my spectrum will have del of F minus 200 plus del of F plus 200. Then this is the first part. Second part is 3 whole into del of f minus 320 plus del of f plus 320. So this is the frequency component. It is determined with respect to g of f. Now we need to represent in frequency spectrum. So that is g of f. So where is the center frequency? 200 and plus 200. So first I need to represent, this is 200 and this is minus 200. Okay. And what is the amplitude? Amplitude is 1. Next one, center frequency is how much? This is 320. So 320 is here. So it is 320. What is the amplitude? Amplitude is 3. So similarly this side, reflection side, so it is minus 320, amplitude is 3. So this is my g of f. Okay. So this all derivation we have done while discussing our sampling theorem. So this f minus 320 means the 320 is the center frequency and you need to identify the side band. Left hand side at this point for this 200, similarly for 320 here and here you can represent the side bands. Okay. So this is called as your representation of g of f. Similarly the sample signal you need to represent. Okay. So that also we will see. So the sample signal, that is g del of f, the basic equation I have to write. What it is? Fs summation n is equals to minus infinity to infinity g of f minus fs. Done. So this is my sample signal, equation for the sample signal. What we have written for our natural sampling, flat top sampling, or it is a instantaneous sampling. Okay. So now here fs is given as 500 Hz. Then you need to substitute here g del x of f is 500 summation n is equals to minus infinite to infinite g of f minus 500 times of n. N is the number of samples. Now we have g of f, that is f minus 200 plus del of f plus 200, one component. Another one, thrice of del of f minus 320 plus del of f plus 320. So that I need to substitute here. So that is f. Now f is shifted to f minus 500n. So what will be my components? So here I will write 500 summation n is equals to minus infinite to infinite for this particular component. So what will be my resultant value? My resultant value is g of f minus 500 n minus 200. That is the first. This is del. Okay. And del of f minus 500 n plus 200. Done. Because f is replaced by f minus 500. So f is replaced means f minus 200 and f plus 200. So f is replaced by f minus 500. So this is the first component. Similarly, second component is 3. 3 into 500 is how much? Or you take this 5 as common. So here it is 3. Summation n is equals to minus infinite to infinite del of f minus 500 n minus 320 plus del of f minus 500 n plus 320. Done. So this is my spectrum for the sample signal. Okay. Now if it is sampled signal for n is equals to 1, what will be your f minus this one, that you have to calculate. If n is equals to minus 1, how much it will be calculated, and then you can represent the sample signal. Okay. So let me represent it. So first I will take 500 n value as plus 1. If n value is plus 1, this 500 and this 200 will become 700. So f minus 700, then here it will become 300, f minus 300. So that I have to represent dot 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 plus del of f minus 700 plus del of, here n is plus 1, so it is f minus 300. Then when n is plus 2, this is 1000 and 800, it will come f minus 800 plus del of, here it is 2000 minus 1000, this is 1200, sorry, this is minus 1200, and here it will be minus del of 800. Okay, this is for 1 and 2. This is when n is equals to 1 and n is equals to 2. Similarly, dot dot dot, for negative side also you can put n is minus 1, so it will become plus. So f plus del of f plus 300 one component, and this one minus 1 is plus. So here I will get del of f minus plus 700 one component. Then this is for n is equals to minus 1. Similarly, you can calculate for n is equals to minus 2. This is plus 2. Similarly, minus 2 also we can calculate. This is for first half. Similarly, for second also, you can put n equals to 1. When it is plus, it will become as 820 and it will become around 180 or 170 or something else it will come. Similarly, if you change these values, plus 1, minus 1, plus 2, minus 2, you will get your spectrums. Spectrum means positions. Okay. So let me draw that particular position for the simplification. So after substituting all those things, you will get this sort of representation. First at 180, second at 200, then at 300, then at 320, all this. Similarly, this is 400, this is the cutoff frequency. This is 500 Hz, that is the sampling frequency. This is amplitude is Fs and this amplitude is 3Fs. You can substitute 500 and 3 times of 500. Okay? So this is 3Fs. Similarly, just the reflection side you need to represent. So this is 3Fs. This is 200, that is Fs. This is 300. Minus 300, this is Fs, and minus 320, that is 3Fs. Then this is minus 400 and then this is minus 500. Okay. So this sort of spectrum it will be generated. So this is the expansion. If you did not to expand it directly also we can represent this. So this is the sample representation. Okay. Now we have to pass this sample signal through the low pass filter, and the low pass filter is having the cutoff frequency or the response of the low pass filter, that is h of f, is having cutoff frequency fc, and this is minus fc. Fc we have given 400 Hz and this is minus 400 Hz. So when this sample signal enters to this low pass filter, what are the spectral components we can identify? Now here you can see that 400 is here as well as here. So if my low pass filter response is up to this much, that means I am not losing my information. All these spectrums are available. So what will be the output? The output will be this whole thing, because 400 is the cutoff frequency. Within that 400, all my spectral components are available, which is less. If it is greater, it will not consider anything. It must be within this particular spectrum. So output of, so here I will draw G out of F. G out of F means the sample signal passed through this low pass filter, we will get this sort of outputs. This is for positive half. Similarly, this is for negative half. Okay, this is 3Fs, this is also 3Fs, this is Fs, this is Fs, 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 3Fs, this is 3Fs. This is 0, this is 180, this is 200, this is 300, and this is 320. Similarly, left hand side also you can represent. So left hand side is minus 180, minus 200, minus 300, minus 320. So these are the frequency spectrum which you will get when the sample signal is passed through this low pass filter, and you will extract the whole information. So this is the case when the sample signal is passes through the low pass filter in order to reconstruct your original modulating signal. So this is your original modulating signal having certain amplitude. Okay, from this signal we can extract our modulating signal. This is the sample signal. From this we can extract. We are not using any sort of frequency component. You can see all frequency components are available. Okay. Okay, so this is one more question. So here you can see, you have to given the question is, consider a signal G of t is a cos 2 pi f naught t. Okay. Plot the spectrum for any discrete time signal, means sample signal, instantaneous signal. G del of t derived by the sampling of G of t at the rate of fs. Tn is equals to n by fs means n into ts. N into ts. Number of samples means we are converting G of t to G of nts, which is also called as G del t. Okay, G del of t. Now, where n is equals to 0, 1, 2, 3 plus minus right hand side as well as left hand side spectral can be represented. Now here the question is, if the sampling is done, Fs is equals to f naught, means whatever the frequency is given, if the sampling frequency is same, then how the spectral component will be? If the sampling is done twice of f naught, then what will be the spectral component? Even Fs is equals to thrice f naught, then what will be my spectral component? So these are the fundamental questions which may come in your exam. So step by step we will see. So first, G of t is equals to a cos 2 pi f naught. We need to sample it. Okay. So if I am doing sampling, then I should get G of f. First I need to identify G of f, then we can go for G del of f. So G of f is a by 2 del of f minus f naught plus del of f plus f naught. Why I am using this Fourier transform? Because it is easy to represent in sampled manner. Okay. Now this is my G of f. I need to calculate G del of f. So G del of f means it is fs summation n is equals to minus infinite to infinite G of f minus n fs. Done. So this is the representation. Now this representation is what? G of f minus n fs. Now according to the given question, fs is equals to f naught, that you have to substitute. Fs is equals to 2 f naught, that you have to substitute. Fs is equals to 3 f naught, that you have to substitute. So for first case, Fs is equals to f naught then G del of F. सर वो रहेगा नीचे, उसको बोल दीजिए ना, मैं आ जाऊंगा 515. So G del of F is equals to F naught summation n is equals to minus infinite to infinite G of F minus F naught. Done. Now if G of F minus F naught, I need to substitute here. So if I will substitute, I will get A F naught by 2 summation n is equals to minus infinite to infinite. First, this is F minus F naught. So here I need to substitute this value. So what I will get? Del of F minus F naught minus F naught. This is first. Second, del of F plus F naught minus F naught plus F naught. Sorry, it is plus n F naught, because this is the negative case. Substitute this value here. So minus, it will become minus, and here it will become plus. Okay. So it is plus, and here it is minus. Now it is correct. So this is the spectral component I will get if I am substituting Fs is equals to F naught. So what will be my spectral component? The spectral component will be G del of F, and the amplitude is how much? A F naught by 2 for all the components. A F naught by 2. So this is first, this is second, this is third, dot dot dot. This is for positions. For what particular position? Let's see. So this is 0, this is F naught, 2 F naught, 3 F naught, this is minus F naught, minus 2 F naught, minus 3 F naught. Now what it is? If you substitute n value as plus, okay? So F naught and this, it will get cancelled out and it will identify 0 position, okay? Similarly, here if F naught, if n is 1, F naught and F naught will be cancelled out, same 0 position it will identify. Done? Similarly, if you substitute n is minus 1, this minus 2 F naught, and here it is plus 1 2 F naught. So this 2 F naught and minus 2 F naught you will get. Similarly, if you substitute n is equals to 3, 1 you will get 3 F naught, 1 you will get minus 3 F naught. So for which particular case? If your sampling frequency is same as F naught. Similarly, you need to represent Fs is equals to 2 F naught. Okay. So for second case, Fs is equals to 2 F naught. Directly I am writing that value, that is G del of F, which is equals to A by 2 F naught in place of Fs, summation n is equals to minus infinite to infinite. Here I will write del of F minus F naught minus 3 n F naught plus del of F plus F naught minus 3 F naught. Okay, so this is plus and this is minus. And your spectral component will be, again, it is G del of F, this is 0. Positions are identified. Substitute the value of n when n is 1, 2, 3 for right hand side, n is minus 1, 2, 3 for left hand side. So you will get 0, this is F naught, then 2 F naught, then 5 F naught, dot dot. Similarly, here you will get minus F naught, minus 2 F naught, and this is minus 5 F naught. And the amplitude is how much? This 2 get cancelled out, A F naught. Done. So these sort of questions may come. And the Fs is equals to 3 F naught that you people have to do. Okay, so that is your task. So this is one sort of question. Okay. Now one more question we will discuss, then we will wind up for today's session, because in the last video 4 portion is left, so the same thing we will continue. So the question is, the spectrum of band pass signal, spectrum of band pass signal G of t, okay, has a bandwidth of 0.8 kilohertz, okay, centered at plus minus 10 kilohertz. Write G of t in terms of in phase and quadrature phase component, in phase and quadrature phase component, okay, and you have to find Fs and Ts, okay. It is a very simple one, okay. So as per the band pass signal, let us consider this is G of F. Sorry, 1 minute. So it is a band pass signal, means it will look like this. This is a particular band and this is also a particular band, and centered at minus 10, centered at plus 10 kilohertz, and the bandwidth is 0.8 kilohertz as it is given. Bandwidth is 0.8 kilohertz, centered at plus minus 10 kilohertz. So this is my G of F. Then I need to represent this one in terms of in phase and quadrature phase. How we will represent? G of t is equals to G I of t cos of 2 pi f naught t minus G Q of t sin of 2 pi f naught t. So this is the in phase and quadrature phase component with respect to the given data. So now here you can see f naught is how much? 10 kilohertz is given, center frequency, because that is the center frequency. So it is 10 kilohertz. Then, and the bandwidth is given as 0.8 kilohertz. Okay. Now, what is the FM? The modulating signal is equals to bandwidth divided by 2. So here I will get 0.4 kilohertz. So this is my modulating frequency. Now once this frequency is known, it is easy to identify Fs and Ts. Fs is what? Fs is equals to twice of Fm, because only one single frequency is available. So Fm is 0.8 kilohertz. Then, so what is your Ts? Ts is equals to 1 by Fs, that is 1 by 0.8, that is 10 by 8, that is 5 by 4 second. Done. So these sort of questions may come in your exam. So for the time being, I will wind up at this point. Next class we will continue few more questions and then we will enter to time division multiplexing. Thank you.